All right, welcome everybody to Friday. We're going to do two recordings today. The first one is going to be a summary of CSI 41, because we've basically covered everything that we're supposed to cover in our data structures class this semester, as well as some more of the more advanced C++ topics. So what we have up on the whiteboard was a list made by the previous class of all the data structures you're supposed to know and all of the C++ topics you're supposed to know. We're going to have a final exam, not a final exam, final competency exam, let's say, in this class. First one will be today. And if you can't make it, then there will be 4 retries on it, so no big deal. The what I'd like for you guys to do now is okay. I want you guys to put into your own words when you would use each one of these data structures. And I want this from each person. And if there's something you don't know when you would use it, like you don't know when you would use a C-style array, which is fair. I basically can't really think of any good uses for a C-style array either. Maybe for backwards compatibility or something. Usually I'm just going to pick a C++ array if I need an array. So I'd like from each of you guys to come up with a use case. Like, imagine you're working for a tech company of some sort. You're working for Microsoft or Wells Fargo's online banking division, whatever, it doesn't matter. And come up with an application, a time when you're like, yes, the correct data structure for this application is a deck, let's say. There is a niche for each one of these data structures. There's a time where you're like, that is the correct data structure, I should be using that. 90% of the time, the answer is going to be either vector or Hashimoto, right? But there are niche cases for all of the other ones. And so the main takeaway that I want you guys to have from this class is knowing when to use each one of these things. And if you come out of this class knowing when you should use a BST, knowing when you should use a heap, knowing when you should use a stack or a queue, then I have been successful as your professor. Don't worry about the C++ stuff. We'll do that in, 10 minutes or so. But for now, I want you to go through all of these, and I want to see every person, give every data structure and write when you would use a vector, when you would use a heap, when you would use a BST. And if you don't know, just say I don't know, and that's fine too. Okay? And then we'll review the ones that most people don't really have a good grasp on, and that'll help prepare you for your final competency exam in this class. So, and the choice of these data structures makes a big difference when it comes to running time. If you're constantly inserting and deleting off the beginning of a vector, you're doing n operations. If you have a billion elements in your vector, you're doing a billion operations when you could be doing one with a deck. And so your code's going to run a billion times slower. Like, that's really bad. If you have the wrong data structure for the job, your code will run much slower than it should. And an experienced computer science person can come in and be like, no, you shouldn't be doing that. In fact, when the electrical engineering department hired me, they knew how to program. They had a program that was working, but they hired me as a computer science junior, I think it was at the time, to come in and essentially clean up their code because it wasn't running very fast. And one of the things that I did was I kind of switched out the algorithm, the data structure that was working, and I took it from like order n cubed to like order 1 time. And then they told me that was not good because it needed to preserve order. So I'm like, okay, so if we need to preserve order, then I can make it order n instead of order n cubed. And then the code went from being dog slow to like pretty fast. And just a little switch out of like the data structure you use can make a tremendous difference to speed. And you need to know what each one of these data structures is good at. None of them are like something you can ignore. Now, I mean, to be fair, like a stack is really just a vector under the hood. It's a vector because you push back and pop back, and that's the stack. But like conceptually, you need to know when can I use a stack? When should I use a stack? And for a queue, conceptually, you need to know when you'd use it. In practice, you would probably use like a deck or something like that to actually implement it. But conceptually, when do I need a queue? When is a good time to use a queue? How should I implement a queue? It could be implemented using a deck. It could be implemented using a circular array. which is kind of like the hash tables. When you like go off the end of a hash table, right? You wrap back around to the beginning. And so with a circular array, you have an array. You got two places, one where you're reading from, one where you're writing to. And as you write data, the right thing advances. And as you read from the thing, that thing advances. And if it ever hits the end, it wraps back around to the beginning again. And you can sit there and read and write out of it unless it completely fills up, in which case you throw an exception and die. Okay, so how's the final going? Sorry I didn't make it to class today. We haven't gone to the final competency exam yet, Lewis. We are we're prepping for it right now. Okay, so I'm going to go ahead and pause the stream now. I want every person online right now, and there are a lot of students here that just don't say anything. I want all of you giving an answer for these 4, 5, 6, 7, 8, 9, maybe 10, 11, if you count more of them. I'm going to pause this for like 10 minutes, by the way, and give me a essay, essentially, or at least a sentence on when you would use each one of these data structures. And then I'm going to go over it when I come back from the pause that starts now. All right, and we're back. So Pool posted this one here. So it's a pretty good sorting of the data structures, I think. God tier, S tier data structures are in fact vectors and hash tables. Hash tables are also called unordered maps, unordered sets, unordered multi-set, unordered multi-map. If you need order one, if you need fast insert, search, delete, it's your boy. Like that's the data structure you need to be using. It is the fastest data structure around. You have a unique key that you can use. Yeah, so if you use a unordered set, the key and the value are actually the same thing. So for example, if you're writing code to check for duplicate words in a paragraph, you don't need to use a map. You can just use an unordered set of strings. You read a string from the paragraph, you put it into the set. Or you check first to see if there's a duplicate. If there's a duplicate, you return, yeah, there's a duplicate. If not, you put it into the set. You grab the next word. Hey, is this one in the set already? Yes, it is. Okay, it's a duplicate. No, put it in. And so you can sit there and very quickly check every time you read a word, seeing if it's a duplicate. And you don't need to use a map for that because the key and the value are the same when you use an unordered set. It's just a set of strings. And it effectively works out the same way. It's the same running time as a map. It's just less what do you call it? Complexity. Like whenever you work with a map and you get a pair back, you're always inserting pairs, you're receiving pairs, and if you don't need it, if you're just making a if you want to write down all the integers you've seen, just a unordered set of integers is really useful. And for example, suppose you want to write code to find out if any two numbers add up to 100. What you can do is you can go through the numbers and add them to the set every time you read a number. And every time you get a new number, you check to see if the 100 minus that number is in the set. So for example, you read 30, you check to see, hey, is 70 in the set already? If it is, 30 plus 70 equals 100, you're done. It's a very simple algorithm. And that's something that like puzzled me. Like when I was a college freshman, like how do you check? You're going to check every number against every other number to see if it adds up to 100. And once you understand hash tables, you're like, that's easy. Just throw it into the hash table. And then every time you read a number, you just check to see if it's subtractive, inverse. I don't know what the math term is for it, but you read a 60, you check to see if 40 is in there. If it is, 60 plus 40 is 100. You're done. If not, you just toss 60 in there. And it's a very simple algorithm. And it's one of the reasons why I teach hash tables to freshmen. When I was a freshman, they did not teach us hash tables. This was a junior level data structure. They did not trust us with the power of the hash and map, which I consider ridiculous. Like I think that hash tables are so darn useful that you gotta get people using them now, so they get really experienced with them later on. They are, I don't think they're that bad. Like I honestly don't understand why. Like you guys can write one. Like I've written them before. It's like this much code. It's really not that bad. Vectors are your basic vanilla ice cream of data structures. If I don't know what kind of data structure I need, I use a vector. And then later on, if I find out that I'm doing a lot of inserts and deletes from the middle or something, then I might switch to like a list in that case. Or if I'm finding out that I'm constantly sorting the vector over and over again, I insert something and sort it, then I'm like, I should probably use a BST in that case. But my kind of starting point for like most of the code that I write is a vector or a hash table. That covers 90% of all my use cases. So all reliable, that's right. Professor, acquire your fastest data structure. My data structures are too fast for you, young one. You cannot, what is it? You cannot begin to comprehend my methods. What was the name for that? I don't remember the name for that. But yeah. So good tiered array. If you're talking about C++ style arrays, then yeah. And they are fast to allocate and deallocate. And the reason for that is because they don't have to go off the heap. Now, most of the time I make a vector like, once, and it's fine. Like if you're worried about speed of like the heap, if you're worried about how fast you can make a vector and you're doing it once in your code, you're worried about the wrong thing. What I'm talking about here when Pool says it's faster than vectors, since they're stack allocated, we're talking about if you're like in a hot loop. Like if you're in a loop, if you're in a function call that gets called 1,000,000 times a second, you most definitely want to avoid using vectors because you're going to be constantly newing and deleting. And those things, they're fast-ish. They're not bad, but they're like, if you're doing it 1,000,000 times a second, it's bad. And so if you're constantly allocating and deallocating like 10 variables, then I would use a stack allocated array. C style array, I'd use a C++ style array to do that. Because C++ style arrays have iterators and they have dot size and things like that. Just make it kind of nice. Stack allocation and deallocation is faster, but that's only a concern in like limited circumstances. They come up. But it's pretty limited. Usually I don't use arrays anymore at all. Linked lists. So that's the list class and the STL. My goals are beyond your. That's the one. Yeah. Thank you. Yeah. That's the one I was thinking of. Okay. So a list class I don't use very often. But yeah, if you insert, if you have a pointer, if you have an iterator to somewhere in the list, you can insert and delete there for order 1. And so sometimes like I non-ironically used a list last month. Like I actually had an algorithm and I was like, a list is actually the correct solution here. And I used it. Like, it's not like I hate them. It's not like I have PTSD from like all the seg faults I got making them over the years. Because I was coding in a year before the STL was implemented. Or maybe it was implemented, I just didn't know about it. But yeah, I still remember the day. I was telling my 12 o'clock class session this. I was sitting on the steps of like Price Center in UC San Diego. And a friend of mine, Brian Dagenhart, like came up to me. He's like, "Hey, have you heard about the STL?" I'm like, "No, what is it?" I was like eating my Panda Express there. Although back then, I think it was before they had Panda. It was like the knockoff, like Panda Express. Anyway, so he's like, "Yeah, they've done all the data structures for you. You don't have to code them yourself anymore." I'm like, "That's cool," because like when we took the class, we had to make our own. Like if you wanted a BST, you got to make it yourself. If you want a linked list, got to make it yourself. And if you have any bugs in it that cause crashes, all your code is going to crash forever because you didn't know how to make a data structure right. So when I took the class, it was all about making the classes and making sure they didn't have bugs in them. Nowadays, it's like you make the class, you can kind of understand it, but you use the standard template library, which is an old term for the standard library, STD. So linked lists, yeah, they come up. Forward list, singly linked list is somebody online actually told me a use for it. They're like one of the few data structures that don't allocate memory if it's empty. And so it's if you're returning, the guy said he has a program where most of the time he returns nothing. And in that case, a forward list is the right thing to return because it doesn't have to do any allocations or anything. It just is essentially returning a null pointer. And I was like, that's actually used for forward list. Cool. There is one. Yep. So singly linked lists, doubly linked lists are typically what I use when I use a list. Decks and queues. So a queue is just a deck with options turned off. But vectors are bad at inserting and deleting at the front. And so a deck has push front and pop front. If you need that, you use a deck, because your vector performance will be garbage if you're constantly inserting and deleting at the beginning. So a deck is literally just a vector where you can insert and delete it at the front. If you don't need that, though, don't use it. Use a vector instead, because decks are slower than vectors. When I benchmarked it, it's about 20 to 30% slower, just in general. So don't use a deck unless you need the functionality of being able to insert and delete at the front. Niche BSTs. Yeah, I would actually say the BSTs are pretty niche. The only reason to use that over a hash table is if you need everything sorted, right? So if you find yourself constantly sorting your data or constantly printing out the data in a sorted fashion, then set or multi-set is your boy. I actually use BSTs a lot in my homework assignments because I can guarantee the order they come out, and that's important for the input tester. Do you guys see that? Like, if I had you guys print all the elements in your, like, that's why for Gilded Rose we didn't have you print all of the database, because it would come out in just whatever order, and I can't input test it, right? So a lot of times I use a set just because then it guarantees everything's sorted, and when you put it into a set and I put it into a set, we're going to get the same results. When you do an unordered set, who knows what order they're going to come out in? It'll fail the test case. So it makes you do like an extra step where you got to copy everything from an unordered set into an ordered set, and then print it, and then throw it away, and this is extra work. So if I don't need the order one performance, which I sometimes don't, like sometimes, we're talking about smallish chunks of data, login is pretty fast. So BSTs are actually pretty fast. For 1 million, the log base 2 of 1 million is 20. Fast. Like that's like 20 is way faster than 1 million. You know what I mean? It's 20 times slower than a hash table, but it is what was that 50,000 times faster than a vector. Yeah. So yeah, sometimes like I'll just do a BST because I'm lazy and I just like having everything sorted always, and I just don't need ultimate performance sometimes. Not often. It is niche. Okay, so heap. Heap, you have a min heap or a max heap. You can't have both at once, I guess. I guess you do too. So yeah, if you're constantly checking minimum, constantly checking maximum, heap is good. And priority queue is the implementation name in the standard library, priority queue. And so it's kind of like a queue where things with higher priority come to the front. And this is actually going to be really useful in CSI 26 if you're constantly trying to find the nearest city. For example, if you're doing pathfinding, the most common algorithm is called Dijkstra's. And what you constantly do is find me the nearest city that I haven't been to before. And then you add that to your network, and then you repeat. Find me the nearest city that I haven't been to before. And so if you put all this stuff into a priority queue, it's very easy. Just give me this nearest city. You go, boop, 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 and you build a route, and you got your fastest route from here to Paris or whatever. Although it might involve some swimming. So stacks. So legit, it is just a vector. It is a useless data structure. Yeah, I would not actually use the standard library stack. Standard library stack and the standard library queue, I would never actually use, except ironically or something. But instead of a queue, I would use a deck because you can push it in the back and pop off the front. But you can do things like print out everything in it, which is really nice and useful for debugging. A stack is literally just the same as a vector, where you push and pop off the end. But a vector, you can print all the elements in it and see what's in there for debugging. But as far as applications go on the stack, let's see what you guys got here. Stack would use for a dictionary. I don't know about that. LIFO, good for reversing the order. Yeah. So a stack is good if you push everything onto the stack and then pop it all off. You get the thing reversed. That is a classic stack use. Another stack I don't know. Stack I don't know. Stack I don't know. Card game like Magic, you can stack. Yeah. So Magic, I cast a spell, you counterspell it, I counterspell it, you counterspell it. And all these things go onto a stack, and then the effects resolve in last and first out order. Undoing and redoing. Yeah, that's a classic one. So Mosed is absolutely right. when you're in Word and you take an action, like you type something, hit return, that goes on to the undo stack. And then you hit Control Z, and then it comes off and it goes back the way it was before. But when it comes off, it actually gets pushed onto a redo stack. And so every time you hit undo, 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 it's building up all these actions on the redo stack. And then if you hit redo, 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 then they come off the redo stack and go onto the undo stack. And then you can go back and forth from your edit history until you find the place where you accidentally deleted your thesis because you were a moron and you did it in Microsoft Word. Just trust me on this one. Don't write your thesis in Microsoft Word. I spent more time reformatting my damn thesis and just wrangling Microsoft's stupid pagination system than I did actually writing my thesis. 100 pages of formatted tables and pictures and learn LaTeX. So LaTeX is by this guy right here. Knuth, if you see that, it's upside down. There we go. Knuth, Donald Knuth is a professor. I think he's probably an emeritus at this point. He's kind of old. He's a professor at Stanford. He's one of the most famous computer scientists ever. And he invented LaTeX, which is what you should learn if you ever do any sort of scientific publications and things like that. So it is beautiful and it creates really nice looking papers. So the font is really nice. And so when people see a paper, they can tell that it's been made in LaTeX. And it just has kind of this aura of like, professionalism about it. When you do your thesis in Microsoft Word, everyone knows you're an idiot. Word is not good. It is really not good. Your mom did her 300-page dissertation in Word. I am sorry, man. Like it is massive pain. Yeah, but if you've never heard of Knuth before, his Art of Computer Programming is an absolute treasure. This is sort of like the computer scientist's Bible, so to speak. And he's working on finishing it, which may or may not ever happen at some point. That set is like $300. It was a present, actually. So I got a nice sister and brother-in-law. My brother-in-law is a computer science guy too. My sister is too. Okay, so stacks. Yeah, so undo, redo. That's great. Parentheses checking. Every time you see an open parentheses, you push it onto the stack. Every time you close parentheses, you pop off the stack until you get a matching parentheses, and then you evaluate everything between. That's a great way of doing algebra. If you get a closed parentheses and there's no open parentheses, then you hit the bottom of the stack, you get a throw an error, mismatched parentheses error, things like that. Compilers use stacks all the time to like keep track of variables, nested scopes and things like that. The stack, literally the stack, and your program is a stack as it stack allocates things. Let's see what else. Yeah, hash tables and vectors are like clutch. Stacks and queues you don't actually use, but you have to understand them conceptually. Like a queue, the most important use for a queue is like anytime you need to buffer data. It's like if somebody's producing data and somebody else is consuming the data and it's not like synchronous, it's not happening at the same time, you need to put a buffer in between them. So for example, if somebody's typing keys on the keyboard, the program might not be ready to receive those keystrokes. So have you guys ever seen a program like freeze for a second, and then when it unfreezes, like all of a sudden all of your letters appear? Like, Microsoft Word does all the time. Right? All of your keystrokes are actually going into a buffer. So it pushes into the back of it. And then when Microsoft Word is ready doing whatever it is doing, it pulls the keys off the front of the queue and then it empties the queue. Networking works the same way. Data comes in from the network, and then when World of Warcraft is ready to read the data out of the queue, it pulls data first in, first out, and it pulls data until the data is empty. and then more data will feed in later, and it'll check later and pull data out of it. So queues conceptually are really important. Anytime you have that asynchronous producer consumer model, you typically stick a queue in between. Anytime you need last and first out anything, stacks conceptually. In practice, though, you're going to use a vector to implement a stack, and you're going to use a deck to implement a queue. Yeah, that's it. And so you guys should be able to tell me what the big O is for the most common operations on all of these things. All right, so let's talk about, what time is it, 3:15. This class gets out at 4:20, so we got like an hour left. Okay, so let's do another thing. I want you guys to type up when you would use each one of these things. When should you use proper class design, right? When is a good time to use inheritance? When is a good time to use templates? When is a good time to use recursion? And the answer is, of course, after you've used recursion is the best time to use recursion. And before you use recursion as well. That's the best time to use recursion as well. So when should you use a lambda? And I know Megan's answer to that one. When should you use a functor? When should you? Yeah, never is exactly. I'm anticipating that one. Or for Voss, his answer was always. So when should you use the standard library? So the STL is the old name for this stuff. So like when we're using the standard library classes and things like that, the old name for that was the STL, and it actually used to be a separate like product you would download. It was free, but you would download it. It wasn't part of the standard. It got incorporated into the standard, but some people still call it the STL, the standard template library, to refer to sort of like the container classes and things like that, and inside of the standard library, and maybe some of the other templated functions as well. But typically you'll hear like, oh, should I learn the STL? And it's like, yeah, you should learn vectors and things like that. It's useful. That's typically what people mean when they say it. It's kind of an old term. Most people just say the standard library now. And sorting. When should you sort things? Okay, so you've never heard of a functor? That is a function object. So let me... So let's say that you're going to sort a vector. We're going to have a vector of integers named vec. It's equal to 10. Friday night functors is right. 30 and 4. So we got a vector here, and we want to sort it. So as we all know, you can call sort vector.begin. I can even do ranges sort and just do that, but vector.begin, vector.end, and this will sort it how? What's this going to print? Is it going to print greatest to smallest or smallest to greatest? What do you think? Yeah. So we'll print out smallest to greatest. Now, if I want to sort it greatest to smallest, I can pass in a third parameter here, right? I can pass in a function. So I can pass in like Bob, and then Bob. Take an integer left-hand side, integer right-hand side, and return left-hand side greater than right-hand side. If we do that, then it's going to sort greatest to smallest. So we can create our own comparison function. But now we've got in our global namespace the word Bob taken up. And maybe at some point somebody else is going to try and make a function named Bob, and it's going to give us a ODR violation, a one definition rule violation. So what we can do instead is we can do this. It's a function Bob is equal to lambda. It's the exact same code. You guys see this? Let's get a semicolon on there. It's the exact same code. But now it's not polluting the global namespace. Bob only exists within main. Neat. So if I don't need Bob anywhere else, I can just make a function here, and I can call Bob. Like, this is actually a function call that I can call. cout Bob by 3, and that's going to print true, right? Which is 1. And so Bob is a function, but it's a function that only exists in our imagination. Sorry, it only exists within main. And so once main is over, Bob goes away, and we don't have to use the name Bob in the global namespace. And in a large project, it's hard keeping track of all the different functions that exist. And if you have a function that only needs to be called once, then why use up one of your names when you don't need to? You just do this. Okay. And you actually don't even need Bob at all. Like, I mean, if you're going to call it a second time or something, then you would need it. But if you're only calling it once, then why even give it a name, right? Let's just do D3W. And over here, we're going to have DW, and then here we are going to control V, D, and P. And we can just actually shove it right inside of here. And then we don't need to even have a functor. We just actually have a lambda declared right in the middle of the sort function if you want. That's perfectly valid. Does that make sense, Aiden? So we could have a global function as our custom sorter. We could have a functor locally in our main or whatever function we're in as our sorter, or we can actually just make a sorter here. And however we tell it to sort, there's not too many options with ints. Greatest to smallest, smallest to greatest is about it. I guess even or odds. That'd be kind of weird. Probably could sort like all the evens first and the odds second. That'd be kind of weird. Okay, yeah. But yeah, or you just do it like this. So those are 3 options of doing the same kind of custom sorting. Okay. So I'm going to go ahead and pause the lecture now. Go ahead, everybody take 10 minutes and tell me when you would use each one of these things up on the whiteboard. And if you don't write anything, then I'm going to at you. So disconnect from chat now so you won't be called out for not participating in class. Because all of you guys, and if you don't know something, just say, I don't know. It's fine. Like, you're students. You're not expected to know, everything. Do I know everything? Hell no. There are large parts of the standard library I don't know. I can't even tell you like what some of these sections like are. Like, there's like mathematical special functions. Like, I've clicked on these things. I don't know what a cylindrical Bessel function of the first kind is, and how does that differ from the regular modified cylindrical. But I don't know. I can't tell you. I don't know what these things are. I've clicked on them, as you can see, and I've like, okay, well, all right, what is it? Computes the regular modified cylindrical Bessel function of nu and x. You can see I've even clicked on the Wikipedia link here. And I'm just like, okay. Close. So, yeah, like I said, like there's functions in the standard library. I don't know what to do, when I would use them. So, don't beat yourself up if you don't know everything. Okay, so I'm going to pause the recording. Everybody get your answers in on chat. I'll give you guys 5-ish minutes or so. Okay, so welcome back. Yeah, so proper class design. Some people say always. I would actually wind that down a little bit. Doing private member variables, getters, setters, constructors, like that's pretty standard practice. That said, there's not too much benefit to using a getter and setter when it's just a regular variable. It's like, you might as well make it public at that point. Like if you don't care what value it has or anything like that. You're just sort of like adding another level of indirection. A lot of times I'll do a getter and setter anyway, just so that all of my interfaces are get set, kinds of things. But there's kind of no downside to using a public member variable. I mean, I guess people might, it might violate separation of concerns, like people will know what your variable names are or whatever. Some people would argue that if you don't care about the value, just make it public. The real benefit of proper class design is invariant protection. So in other words, let's say that your temperature has to range from like negative 270 degrees Celsius. What is absolute value? Negative 270? Negative 273. Okay. So like if you have a temperature in Celsius, like the lowest value it can have is like negative 273, right? And so if somebody types in like the temperature is negative 400, like that doesn't make any sense, right? So that's an invariant. An invariant is something that must always be true of your class. And if your variables are public, you can't enforce that invariant. And so really the reason to use proper class design is when there is an invariant you're trying to protect. The temperature cannot be below negative 273.15. Okay. That's really the invariants are like vetting. You vet to make sure that the invariant is preserved. So when somebody calls set temperature on you, when they call set temperature, you vet there to make sure that the temperature going in is not below absolute zero. Okay. And so your invariant is a promise that you make. An invariant is a contract that you have. You say the temperature will never be below absolute zero, I swear it. If your variable was public, you cannot guarantee that because somebody could just set it to negative 600. But if you have a getter and a setter, then your setter can like verify when they try changing the temperature that it's not dropping below absolute zero. So that's really the reason why we use proper class design. Is a lot of times there are things that you guarantee to be true, and that's how you fulfill your guarantee, how you make your promise. Inheritance is like when you have two classes that are very similar and you don't want to repeat yourself. So I'll say that again. If you have two classes that are like 99% the same, you probably are going to want to use inheritance one way or the other. Either A inherits from B or B inherits from A, or they both inherit from some common shared class. Because when you start making all these different variants of classes and you're just copying and pasting huge swathes of code, that's usually a sign you should be using either inheritance or templates. And inheritance and templates are both different ways of kind of attacking the same problem. Inheritance we use when things have a is-a relationship, like we always use animals, right? So like a dog is a mammal and a mammal is a human. When you have that kind of relationship, we use inheritance. Templates we use to don't repeat yourself a different way. When you want to have a function that works with like any numeric type, we use a templated function. C does not have templates, and you can see in C how bad it is. So the C math library is the literal math.h from the C language, and they've huge value. I love it. And so they've got all these different versions of like these different functions that are just like all variants of each other that should just be templated, honestly, right? So let's see, square root. Let's see, where's absolute value? So you got abs, you got fabs, you got fabs f, you got fabs l. It's like, what's the difference? Like to me, all of them should just be abs. Like, and just template it. And so fabs is the double version of it, and fabs f is the float version of it. So you'd think the f in fab stands for float, and you'd be wrong. Fabs should be called dabs, right? Because it's the double version of abs. And so then they have fabs f for the float version of, yeah. And then you have fabsl. It's the long double. It doesn't make sense. Just make an absolute value function. Like, come on. But the C language doesn't have templates. So that's why they have 900 million different functions for everything. And that's actually why the standard library got invented. A guy named Alexander Stepanov was working in, I think, St. Petersburg when he got like food poisoning. His job was to just make all these different versions of the same function over and over again. He's like, it'd be really neat if I could just write the function once and not like a bunch of times. And that's where templates came from. And that's where the STL came from. That was his work too. So if I ever see him, I'll buy him a beer. All right. Sorting. Yeah, sorting is useful. Comes up a lot. So lambdas, we just talked about that earlier. Lambdas are anonymous functions. You can save them into a variable if you want, or you can just use them one time. If you need a one-off function, they're pretty useful for that. And recursion takes place whenever you have the self-similarity principle. Anytime you've got like a tree, like a binary tree. Every subtree of a tree is a tree. And the subtree of that tree is a tree. And so that's self-similar. Every child of a linked list is a linked list. And so you can write a lot of your programs without using like a for loop or a while loop or something like that if you do it recursively. And is that good? I would say no, actually. But, you know, I saw a guy online who's like, I haven't written a for loop in 20 years, you know. Like, okay. There's nothing wrong with a for loop, but, you know, you do you. Yeah, macros. No, like in the standard library, there's like a for each function. And so like you can use that instead of a for loop. C++. And so like they're like, I just use the standard library for everything, you know. So look, there's a lambda. So for each print, right? So this is like a range-based for loop to print. Is that better looking than a range-based for loop to print a vector of integers? No. But congratulations, you have not used a for loop. You've used a for each function. Well done. Here, it's going to, for each of the elements in the vector, it is going to increment them by 1. Is that better than a for loop that increments all the elements by 1? No. But congratulations, you have avoided using a for loop again. So, yeah, everybody's got their own style, I guess. I don't know. He's one of the moderators of the C++ Reddit, too. Redding. So, would you recommend that rather than writing a for loop? I would not. I think it looks not great. You know, like you just saw they had a for each loop like that. I think this looks a lot better, honestly. Than, you know, what was it? For each vector dot begin, vector dot end, lambda, int x, cout x. Like, it's substantially more typing, you know what I mean? Substantially more typing, you know. It's less readable. I don't know. Everyone's got their own style, you know what I mean? Like, they do. And if Redding likes not writing for loops, then more power to him. You know, it's like, knock yourself out. Everybody's got opinions on style, and it's like, you know, like you can definitely tell when there's bad style, good style, what's the best style. You know, I'm fairly agnostic on it. I can work with anything. The text doesn't light up also. What's considered bad style? Who's got the coding drip? I would argue the GNU project's coding style is pretty bad. It looks pretty terrible, at least in my opinion, the GNU coding standards. Like, look at that. Like, look at that formatting. Like, yeah, nah, not a fan. I mean, I like Richard Stallman and everything, but yeah, that's some bad coding. That's minified. That's minified code. Yeah, they got probably too many indentation levels here. The Linux kernel says if you ever indent more than about 4 times, your code's probably wrong. So it's, you know, there are times, but So like I said, like, okay, you don't want to write for loops, knock yourself out. Like, I'm not gonna. Yeah, I can't complain too much. I've got my way of doing things. Other people have their way of doing things. There's no like intrinsic difference between these two options here. Okay, so that is it for our overview of CSI 41. Congratulations, you guys have all finished the class. You have completed the Crucible of Souls. We had about 11 students drop out of this class or so. So maybe more, I don't know. And online is harder, definitely, than in person because there's that lack of like personal connection, things like that. So give yourselves a round of applause for successfully completing it. Over the next 2 weeks, we will finish out our competency exams, and we will do some fun topics like multi-threading and networking and things like that. So please clap. Hey, clap for yourself. You don't need to clap for me. And with that, I will stop the recording here and move on to your first final competency exam. All right. You go over bit masking and bits. Oh yeah. Let's do that. That's a good topic. Okay. That'll be next week.